Suppose we want to solve a congruence equation of this form. So we want to solve this congruence. We want to find x such that x plus 7 is congruent to 3 mod 17. In other words, also, if we take x plus 7 and we divide by 17, the remainder should be 3, right? So how can we solve something like this? So we can think of this again as the clock with 17. We can think of it in terms of Z17 and do operations there on that clock. And in this case, we can treat the thing pretty much like we normally would. So for example, let's subtract 7 on both sides. So let's subtract 7 on both sides. And what we get is then x plus 7 minus 7 will be just x. So this is going to be congruent to 3 minus 7, which will be congruent to minus 4. Now, what is minus 4 on the clock with 17? So if you have a clock that goes from 0 here, and you have 16, you have 1, minus 4 is going minus 4 in this direction, so you'll go 16, 15, 14, 13. So the minus 4 is just 13 in the clock arithmetic. So this is going to be 13 mod 17, and this is our solution. So it's x congruent to 13 mod 17. And of course, we can always check. So if you do 13 plus 7, this is going to be, so 13 plus 7 is 20. And if you divide 20 by 17, the remainder will be 3. So this is congruent to 3 mod 17. Okay, so we were able to solve this equation. Let's look at a different equation. Let's say we want to solve 2x plus 7 congruent to 3 mod 17. Well, we can again do that first step to subtract 7 on both sides. And now we get 2x congruent to 13. But now the issue is, what we would like to do is divide by 2. But what does it mean to divide by 2 modulo 17, right? How can we do that? And maybe one way you can think about this is, what does it mean to divide by 2? It means that there's a number, so sometimes we write it as half, sometimes we write it as 2 to the minus 1, right? So there has to exist this 2 to the minus 1, that when you multiply 2 to the minus 1, you get a 1. But now we want this mod 17. So we were asking, what is this number? What is 2 to the minus 1? What number do you multiply by 2 and you get a 1 mod 17? Because then if we multiplied on both sides, we would be able to get rid of this 2. And then we have two questions. One is, how do we find that number? I mean, you can always find by inspection, but there's even the question, does that number exist, right? Is it always the case that you can divide by 2 modulo 17? What about modulo 4? What about modulo 9, right? Can you always divide by numbers? So let's take a look at that. So what is the multiplicative inverse modulo n? So if you have a and n integers with n larger than 1, the multiplicative inverse of a modulo n is going to be this number here that satisfies the property that when you multiply it by a, you get 1 mod n. So for example, if you do 5 times 3, right, so this is 15, which will be 1 mod 7. So what is the remainder of 15 mod 7? So it's 7 times 2, 14 plus 1, so it's 1. What this means is that 5, so the inverse of 5 is just 3. mod 7. And the other way around, the inverse of 3 is 5 mod 7. And so if we're working in mod 7 and you're wanting to solve an equation or something that has a 5 times something and you want to make it into a 1, you can just multiply by 3. And if you want to make the 3 into a 1, you multiply by 5. Okay. Now, do these always exist? How do we deal with them? Let's think about this. So let's look at some cases. So if we write out the Z2, let's work over mod 2. So mod 2 is the clock with two numbers, and we can fill out the addition table. So 0 plus 0 is 0, 0 plus 1, 1, 0 plus 1, 1. 1 plus 1 is 2, which when divided by 2 has the remainder 0, or in other words, again, 1 plus 1 will take you to 0 here. Let's do the multiplication. So when you multiply by 0, you always get 0. 1 times 1 is 1. And so of course you can never invert 0, and because you can never divide by 0, and that still is true in Zn, but can you invert all the other numbers, right? So in this case, Z2 has only two numbers, 0 and 1. And so we are asking, does 1 have an inverse? And if you go to the multiplication table, it does. 1 is the inverse of itself. And I mean, that's actually going to be true always for every Zn. But okay, the point is that in Z2, you don't need to worry about inverses. Every time you need to do an inverse in Z2, you can do it. And so that's quite nice. Let's look at Z3. So let's do the addition table, why not? So 0 plus 0, 0 plus 1, 0 plus 2 is 2, and here 1, 2. 1 plus 1 is 2, nothing new there. 2 plus 1 is 3, and now of course 3 is 0 in Z3. So plus 2 here, you end up here. So this is just 0 and 0. 2 plus 2 is 4, which is 1. So 1, 2, 3, 4, right? Or you can think of it as 2 plus 2 is going to be the 4 here. Or 4 divided by 3 has a remainder of 1. So all of those things are equivalent. But we're interested in the multiplication here. Will every element have an inverse? So 0 times anything is 0. 1 times 1 is 1, and so actually it will be an inverse of itself. 1 times 2 is 2, 1 times 2 is 2. And will 2 have an inverse? Well, that's actually going to depend on this value here, because for 2 to have an inverse, we have to be able to multiply it by something and get a 1. And there's only one candidate here. So what is 2 times 2? It's going to be 4. And the remainder of 4, when you divide by 3, is 1. So it actually will be a 1. And so yeah, in this case, every non-zero element of Z3 has an inverse. So the inverse, let's write it in the middle here. So the inverse, or down here, the inverse of 1 is always 1. But the inverse of 2 here is going to be just 2 itself. So if you multiply in Z3 by 2 by 2, you get 1. Okay. Let's do Z4. And let's fill in the addition table. Always good. So when you add by 0, you just keep the same number. So nothing there. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4, and that's where things are different than the integers, because 4 here is 0, right? So 1 plus 3 is 4, which is 0. So 1 plus 2 is 3. 1 plus 3 is 4, which is 0. 2 plus 2 is 4, which we already saw, that is 0. 3 plus 2 is 5. So 3 plus 2 is 5, which is 1 here. And so if you divide 5 by 4, you get a remainder of 1. And 3 plus 3 is 6. And 6 is going to be this 2 over here, right? Because if you divide 6 by 4, you get a remainder of 2. So it's 1, 2, 3, 4, 5, 6. So it'll be 2. But what we care about here is the multiplication. Will it be the case that every number has an inverse? So when we multiply by 0, we get this here. When we multiply by 1, we keep the same number, 1, 2, 3, 1, 2, 3. And so, of course, 1 has an inverse. So the inverse of 1 is equal to 1, because if you look here, there is a 1 here, which is when 1 multiplies by 1. Okay. Does 2 have an inverse? Let's see. So if we do 2 times 2, we get 4. 4 here is equal to 0, right? 2 times 2 is 4. This is equal to 0. And now 2 times 3 is 6, which divided by 4 has a remainder 2. So that's equal to 2. So that actually means that there is no inverse for 2. So 2 here does not exist. This means that if we say, oh, solve the equation 2x congruent to 1 mod 4, this has no solutions. So it's not true that you can solve any equation like this, because there is no number that you multiply by 2 and gets you a 1. There's no way for you to multiply on both sides here to get rid of this 2 here. This just doesn't happen. And you can also look at this row here. Every number when you multiply by 2, it's either going to be 0 or 2. So also you can't solve the equation 2x equal to 3, for example. Okay, what about for 3? So 3 times 2 is 6, which is 2. And 3 times 3 is 9. 9 divided by 4 is going to be 4 times 2 plus 1. So it's going to be a 1 here. And so 3 does have an inverse. So 3 does have an inverse in Z4, which is just going to be itself, 3. So if you need to multiply, if you're solving some system, let's say you're solving 3x plus 2 congruent 3 mod 4. So you subtract by 2 on both sides, you get 3x congruent to 1 mod 4. And now if you multiply by 3, you get x congruent to 3 mod 4. And so you're able to solve any type of equation if you need to divide by 3, but not by 2. Things with 2 in Z4 are not going to work. And so it's not true that when you're doing modular arithmetic that it's always the case that you can invert. And so when is it that you can invert, right? Like, let's say on the clock with 12, what are the elements here that have an inverse? And how can we think about that? And so if you go back to 4, the issue was with 2. And you can notice that this issue happens because 2 and 4, they're not co-prime. They share divisors. And what do I mean? So in this case, just 2 divides 4. And so the idea is that if 2 divides 4, then if you go by 2s, you're going to end up at 0. And then the next number you're going to go to is 2. And so you're never going to hit 1. And so we can see an example here. So for example, 2 here divides 12. So if I go by 2s, so 2, 2 times 2, 2 times 3, 2 times 4, 2 times 5, 2 times 6, I'm here. 2 times 7, I'm going to be at 2, and this just repeats. And so there's no way to multiply by 2 here so that you end up at 1. Notice that 3 also divides 12. And so if you go by 3s, 3, 6, 9, 12, 3, 6, 9, 12, you're never going to reach 1. So there's no way. So here, if we list them, So 2 to the minus 1 does not exist. So let's say no 2 to the minus 1, no 3 to the minus 1, right? Let's look at 4. 4 also divides 12, so it's going to be 4, 8, 12, 4, 8, 12. So you never get a 1. So there's not going to be any 4 to the minus 1. What about 5? 5 does not divide 12. So if you go by 5s, you'll go 5, 10, then 1, 2, 3, 4, 5, then 1, 2, 3, 4, 5, then 1, 2, 3, 4, 5. Oh, there is a number that you multiply by 5. So the inverse of 5, and we can actually find it here. So 5 times 1, 5 times 2, and then 1, 2, 3, 4, 5. This is 5 times 3. 1, 2, 3, 4, 5. This is 5 times 4. 1, 2, 3, 4, 5. This is 5 times 5. So it's going to be 5 itself here. So if you multiply 5 by 5, you get 25. And 25, when you divide by 12, gives you 1 modulo 12, right? Okay, what about 6? 6 divides 12, so there's not going to be any, so no 6 to the minus 1, because again, you're going to be 6, 12, 6, 12. 7 does not divide 12, and you'll see that if you go, you will find an inverse. So 7, then 1, 2, so this is 1, 7, then 7, then 1, 2, 3, 4, 5, 6, 7. This is 2 7s. 1, 2, 3, 4, 5, 6, 7. This is 3 7s. 1, 2, 3, 4, 5, 6, 7. This is 4 7s. 1, 2, 3, 4, 5, 6, 7. 5 7s. 1, 2, 3, 4, 5, 6, 7. 6 7s. 1, 2, 3, 4, 5, 6, 7. So 7 7s. So here the inverse of 7 is equal to 7. And so if you do 7 times 7, you get 49. And if you divide 49 by 12, so let's think. So 49 by 12, so 49 is going to be equal to, let's say, 12 times 3 or times 4, times 3 probably, or so 12 times 4, 48. So this is going to be 12 times 4 plus 1, and so you can see that this is the inverse. And if you go 8, it's not co-prime with this, so you will end up at the 0 here. So 8, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 at 0. And so that means the next time you add, you're back at 8, so you're never going to be able to reach 1, right? So the criteria here is being co-prime with the number of numbers in the clock here. And so we can write that as a theorem. So an integer a has a multiplicative inverse modulo n if and only if the GCD of a and n is equal to 1. Not only that, so we saw that we can find the GCD with the Euclidean algorithm, but remember that by Bezout's theorem, you could write your GCD as a combination of these two numbers here. So you can actually use the extended Euclidean algorithm to find the numbers that give you this. And now if you find the numbers that give you this, so notice that if you write, let's say you wrote your number, you know that AS plus NT is congruent to 1 because it's equal to 1 mod n. But n is just 0, so this is just AS. And so this means that your number A here, this S is its inverse. So how do you find the inverse of a number modulo n, well, you can do the extended Euclidean algorithm, and if the GCD is not 1, there will be no inverse. If the GCD is 1, then use the extended Euclidean algorithm to find the linear combination that we talked about in Bizot's theorem. And this S that you find here is that inverse. So this gives us the algorithm. And so let's apply all of this. So let's get back to what we wanted to solve. So we wanted to solve this. We subtract by 7, and now we have this issue of 2x congruent to 13 mod 17. Of course, these numbers are small, so you could go and check all possibilities until you find it. But what if these numbers were huge, right? So let's show how we can do this with the extended Euclidean algorithm. So what we do is we want to find the GCD, so we want to apply this of 2 and n here. So we want GCD of 2 and 17. And so how does this work? You take the largest number, 17, and you divide it by the smaller one. And so this is going to be 8 times 2 plus 1. Then you take, this number here, and you divide by this. So this will be the 8 is going to be equal to, when you divide, it's just going to be 8 times 1 plus 0. And so this means that the GCD is this number over here, right? It's the remainder, the non-zero remainder before the 0 happens. So here it's just going to be equal to 1. Okay, so since the GCD here of 2 and 17 is equal to 1, this means that it exists. So there is a multiplicative inverse. Now, how can we find it? We just need to find this number here. So when we do the extended Euclidean algorithm, we do back substitution. In this case, there's only one equation, so we just write this 1 equal to, and we rewrite these to the side. So this will just be, let me write it here, 1 is going to be equal to 17 minus 8 times 2. And so this number here, and let me write it like this, 17 plus minus 8 times 2. And so this number over here, because again, remember, we are interested in writing 1 as a combination of a and n. A is 2, n is 17, and we want to find this s here. So 1 is a combination of 17 and 2, and this is our s. It's our minus 8. So this means that minus 8 is our inverse, is equal to the 2 inverse mod 17. And so what is minus 8 mod 17? So minus 8 mod 17, so if you do the clock with the 0 here and you go 8 in this direction, it's just going to be 9. So this will be 9 mod 17, which means that the inverse of 2 here, let me write this mod correctly, which means that the inverse of 2 is 9 mod 17. And we can check this. If you multiply, so we want to solve this equation here. So let's multiply by 9 on both sides. So we get 18x congruent. So now we do 9 times 13. So 9 times 13 is going to be equal to 117. So 9 times 13, which is 117. And if you divide that by 17, this will give you a remainder of 15 mod 17. And of course, 18 is just 1. So this is just x congruent to 15 mod 17. And then you can just check if you do So our answer then, I'll put it here on the side here, just x congruent to 15 mod 17. And you can always check if you do, like you can replace it here. If you do 15 times 2, it'll give you 30 plus 7, 37. And if you divide 37 by 17, you'll get a remainder of 3. So it'll check out.